Hello everyone, welcome to the electromechanical devices course. In today's video we're going to continue the chapter 4 about the transients. We started this chapter the previous video and we already introduced these different forms and different types, which are the very common types of electrical circuit, the RLC, RL and RC circuits, where we said that L stands for the resistance, L stands for the inductance, C stands for the capacitance of the electrical circuit. And we said that these R and L and C, this would be considered as the equivalent of all of the resistors, the equivalent of all of the capacitors and the inductors within the electrical circuit. So we can combine all of them in just one R, just one C, just one L, and then we can do analysis to this equivalent electrical circuit instead of doing the analysis to the original electrical circuit, which would be hectic, especially in terms of solving the equations or the electrical circuit equation. So generally we said that in case that we have RLC circuit, we're going to end up with a second order equation or second order ordinary differential equation, which this ODE is commonly known as the electric circuit equation. This is the equation that mathematically represent this electric circuit. RL or RC, for either one, we're going to end up with a first order ODE. And these ODEs would be homogeneous or non-homogeneous depending on the right hand side, as we mentioned or as we discussed in the previous video. If the right hand side has a value, it means that this is homogeneous, non-homogeneous ODE. If there is no value, so it is commonly known as non-homogeneous ODE. So we drive where I stands for the current, dt square, and R, this is the resistance, C the capacitance, and Vs stands for the voltage source. That would be variable here depending on the time. So we're going to end up, it means that the right hand side will have a value, so we're going to end up with a non-homogeneous ODE. For the case we mentioned, for the case Vc is 0, it's constant, so we're going to end up with this right hand side is going to be 0. For RC, we're going to end up with just first order ODE, and that's why we already have here the first derivative of the current. And in this case, we're going to end up with this equation in case that there is no capacitors, just L, R, and L. So where the right hand side is going to be Vs. It doesn't matter whatever this Vs is constant or variable. Anyway, we're going to end up with a non-homogeneous ODE. For the RC, it's going to be this one. For the case of DC, VC is DC is constant, we're going to end up with the right hand side is 0 in case that it is variable, so it will be with a value, so we're going to end up with a non-homogeneous ODE. So now the objective is just to show you, and this is the objective of today's video actually, is to show you how we can solve these different forms, different types of the ODEs. As I mentioned, we do have 3 types of ODEs, but we can group them into just two types. Why? Because the first one is second order ODE. These two are first order ODE. So we can say that what I'm gonna do here, I'm just gonna refresh your mind of the way of solving the first order ODEs, and also how we can solve the second order, because this is just second order ODE. All right, so it means that we're just gonna work purely mathematics, just to show you, to refresh your mind how we can solve a first order ODE, and this is the first thing that I'm gonna start with. So starting here with solving first order ODEs. Again, ODE stands for the ordinary differential equations, right? So any first order ODE, we can generally write this equation, since we are interested here in either. As I mentioned, in many of the cases Vs will be given. It means that generally the objective is just to solve the ODE for the current. like this one, for example, like this one. But if we consider this ODE, it would be solved for either Vs or I, the current. If we decided to solve this one for the current, still it is a first order ODE, and we have to deal with it in this way because the current is unknown and we don't have the first derivative of the current. The same thing here, if the current is given and we are interested in finding a solution for the Vs, it is still a first order ODE, and we're gonna apply almost the same approach. So no matter what, whatever for this equation, for the third one, for this RC circuit, no matter what the unknown is, if it is current or if it is voltage source, we still gonna deal with this equation as a first order ODE. But for this one, for example, if the current is given, this is just a linear algebraic equation that can be simply solved. There is no need to deal with this one as ODE because definitely it will not be an ODE anymore, right? It's just gonna be a linear equation that can be simply solved for the voltage source, right? But for this one, no matter what the unknown is, if it is current or voltage, anyway, we're gonna end up with an ODE that should be solved. So that's why let us discuss here how we can solve the first order ODE, and let us assume that the unknown is the current for this case. So this general form, this general equation, this is the one that we're gonna consider. We can rewrite this equation into another form. Generally, here we are talking about mathematics. Like I can write this one as di of t by dt plus y over tau I of t equals f of t. So we could say that this is a general form. This is a general expression. Generally, any first order ODE, we can express this ODE into this form where I should be the variable that you are seeking. This is this equation should be solved for I. If it should be solved for Vs, so you have to replace Vi or swap the Vi with Vs. Make sense? I with the Vs. So what is this tau? What is this f of t? Tau simply it is commonly known as tau. It is commonly known as a time constant. This is time constant parameter, just a constant. And the f of t is known as the source function. This is the source function, which in many of the cases is going to be the Vs, right? Function or related to the Vs. It is not necessary to be the Vs. In this case, it's going to be dVs by dt divided by R, by the way. So, but we're going to discuss this one. But generally, this is a general expression. We can write any first order ODE, whatever this one or this one, we can write these ODEs into this form, simply. So this f of t, it's going to be the, it would be named or given a name as a source function. Also, it would be considered as a forcing in terms of mechanical aspects, since we are mechanical engineers. So it would be considered as the forcing function. Make sense? So these just the names, but we can drive this tau and f of t for these two first order ODEs. So how much is the f of t, how much is the tau for this ODE or this ODE, I'm going to let you know. So simply, your objective is just to make the coefficient of the di by dt just 1 for any one of these two equations. So for example, starting with the RL circuit, to make this coefficient 1, you have to divide all the terms, all the equation by L, right? So this is gonna give us the other, we already like kind of replacing or rewriting again this equation into this equivalent form to come up with a value of f of t, how much is tau. Make sense? So the key idea here is just to try to, once you drive the first order ODE, your objective is just to convert this ODE into this form. Rewrite this ODE into this form. How can I do this? Simply make the coefficient of the di by dt, the first derivative of the current, to be 1. Very simple. So in this case, I'm going to divide by R. In this equation, I'm going to divide, here I'm going to divide by L. Here I'm going to divide by R, right? So starting with the first equation, for example, how much is tau and f of t? So let us split it here into this way. Like assume that we do have RL circuit, and here we do have the RC circuit. So for the RL circuit, if you decided to divide by L to make this coefficient just 1, so it means that we're going to end up with di by dt plus R over L, I of t equals Vs over L. You're going to divide all the terms by L. So this is going to give us, simply, we can do it here just for your reference, by L, by L, by L, right? So we're going to end up with this equation here for the RL di of t by dt plus the R over L I of t equals Vs of t divided by L. Make sense? For the RC circuit, we're gonna do the same. We're just gonna divide all the terms by R. Why R? Because I need this coefficient to be 1 to be consistent with this form. So dividing by R, dividing by R. So you're gonna divide here by R, all the terms. So we're gonna end up with this coefficient here is 1 over RC. This coefficient is going to be just 1 over R in addition to the derivative. So we're going to end up with this equation as di of t by dt plus the 1 over RC I of t equals the 1 over R dVs by dt, where Vs definitely is going to be a function of time, right? So simply comparing this equation, if I ask you to compare this equation to this one, so the first term is di by dt, the first term is di by dt. The second term, it should be something which is 1 over tau times I. Here it's going to be R over L times I. So from here we can conclude that 1 over tau, it should equal to the R over L if you just compare. So since we can conclude that simply tau is going to be L over R in case generally tau, which is the time constant, is going to be the L divided by R. L, the inductance, R is going to be the resistance of the resistor of the electrical circuit that include just L, R, and L. Make sense? For the RC, yes, this is for the R over L. How about this term? The right-hand side here, it is F of t. So we're going to conclude that Vs over L, this gives F of t. So definitely, generally, the forcing term for the RL circuit is going to be Vs of t divided by L. Very simple. So just compare the two equations, you're going to end up with tau. You're going to specify how much is tau, how much is F in terms of the voltage source, in terms of the inductance of the inductor, and in terms of the capacitance. Let us do the same for the RC. We're going to end up that 1 over tau equals 1 over R. So 1 over tau equals 1 over R. The cross multiplication of this equation, we're going to end up that tau, it's going to be R times C. This is the time constant. The forcing term is going to be the right-hand side. So definitely the F of t is going to be the 1 over R dVs of t by dt. Make sense? So simply we're going to conclude that any first order ODE, either this one or this one, we can simply rewrite this ODE into the general form, and we can simply find tau, how much it is in terms of R or C or L, and the forcing term in terms of the Vs. Make sense? Now the objective is just to solve this equation. Now we're going to work mathematical things. So how we can solve the first order ODE? So what I'm going to do here, I'm just going to give you the derivation, the formulation, or the derivation of the solution of our test equation. Then I'm going to give you the general expression at the end that you should use all the time. All right. So let us start with this equation again, which is I of t divided by dt plus 1 over tau I of t equals F of t. This is the general form of the ODE. Right? Okay, and let us give this one as star equation, for example. So the general solution, as a general solution of equation star, it can be split into two parts. General solution of this one, or solving this equation, it should be solved for the I of t. So to solve this equation, it means that what is the expression? It's just to find a function that for the current I of t. To solve this equation, it should be solved for the current. So what does it mean solve it for the current? It means that what is the function of I of t? How much is I of t? Right? So generally we can decompose the solution or the I of t into two terms. One is homogeneous and one is particular. So P stands for particular, H stands for homogeneous. And this is commonly known, if you remember from the mathematics class, that this term is known as the homogeneous solution of the problem. And this one is known as the particular solution of the problem. Make sense? So the IB, this is the particular solution, the IH, this is the homogeneous solution. We can give this one, the homogeneous solution, as a steady state. This is another name, steady state solution, steady state solution. And this is the name that we needed, especially in chapter 5 of this textbook. Chapter 5, we're gonna move to the steady state analysis of electrical circuit. But chapter 4, we are discussing the transient analysis or the transient behavior of the electrical circuit, which is related, I'm sorry, I messed up. I'm sorry, the steady state solution, it should be the particular solution, my bad. So the particular solution is the steady state solution, right? The steady state solution is the particular solution, and this is what we are going to cover through chapter 5. But the homogeneous solution, this is also known as the transient solution, and this is the name or the title of this chapter, which is chapter 4. So through chapter 4, we are interested in investigating this transient behavior of the electrical circuit. So to study the transient behavior of the electrical circuit, it means that you should find the homogeneous solution of this ODE. If we are interested in studying the steady state behavior of the electrical circuit, we should find the particular solution of the ODE. So again, the particular solution, this is commonly known as the steady state solution. So mathematically speaking, we give it a name as particular solution and homogeneous solution. But in terms of application side, whatever mechanical or electrical engineering, since we are working in electrical circuit, so within the electrical circuit, the homogeneous solution, this is the transient solution. Or this is the solution that needed to study the transient behavior of the electrical circuit. The same thing, the particular solution, this is the solution that is needed to study the steady state behavior of the electrical circuit, and this is going to be our interest in chapter 5. So chapter 5, it talks about the steady state analysis of electrical circuit. Chapter 4 talks about the transient analysis of electrical circuit. Make sense? So generally, since we are brought in here the transient and the steady state solution, there should be in here, right? So simply, if for some reason, if we decided to draw, let me just give you a tentative shape or like a rough schematic of this I of t, the total current over time. So because of the homogeneous solution, initially, for example, the time it would be starting with some initial value. So the current, it would be like deviating, assume that it's going to deviate over time somehow till it's gonna be stable. Like as you can see, the current changes over time, severely changes. The change in the current over the time, it is tough, it is hard, it is very dense or intense. Make sense? It means that severely changes or highly changes over time till after a while, after a few seconds, it will reach almost to a very negligible deviation. It still deviates with respect to the time, but this deviation is very negligible. So as you can see, we can split this curve. So simply, if we solve this equation, and we didn't drive the solution yet, when we drive the solution of this equation, the solution, if we decided to plot this solution, it will be plotted into a similar function or a similar curve like this one. So as you can see, this curve can be split into two regions. The first region on the left, as you can see, we have a severe change of the current over time. But here on the right, the change of the current over time is very negligible, definitely compared to the previous region. So within this region on the left, this is known as the transient behavior of the current. How the current changes over time just after we close the electrical circuit, as I'm going to show you. On the right, this is the steady state solution. This is the steady state behavior of the current. So that's why we already splitting the total current into two parts, into a homogeneous solution or transient solution in addition to the steady state solution. The steady state solution, which is related to this part, the transient solution is related to this part. Make sense? And this is going to be very clear. If you open, for example, for any first order ODE or second order ODE, once we solve, we didn't know how we can solve this equation yet, but if we solve and we end up with a function of the current, we decided to plot this function using MATLAB, as I'm going to show you how we can plot these functions using MATLAB. Once we plot these functions, we're going to end up with a curve, which is similar to this one, right? This curve, you can simply, once you just observe the curve, you can simply split it into two regions. There is one region in which the current is severely changes over time, and there is another region that is steadily, or the current almost became steady. It means steady, it means that all the change in the current over time is very negligible, definitely in comparison to the previous region. So we can split this curve into two regions. One is transient, commonly known as the transient, and the second one is the steady state. Through chapter 4, we are interested in studying the transient behavior. This is what we already covering chapter 4, or studying generally in chapter 4. Chapter 5, we are interested more on the steady state, right? So the objective here for this part is just to find the solution, and if we plot the solution, we shall end up with a similar curve, kind of. Right, especially this is going to be a typical thing for the second order ODE, but it's going to be much more clear to understand through the second order ODE. But anyway, whatever it is, first order ODE or second order ODE, you're going to end up with a curve or a solution that can be split into homogeneous or particular. This is mathematically speaking, or transient solution and steady state solution. This is the based on the electrical engineering concept, right? What is the transient behavior of the electrical circuit? Assume that you do have an electrical circuit like this one, and there is a switch here, and this is a volt, Vs, this is the voltage source, and you do have some electrical element like coil L, like R, like even capacitance, if we are talking in general, right? It is not necessary to be just first order ODE. It would be second order ODE like this one. At the instant, initially, the current within all of these electrical elements, it should be zero, right? There is no current within this electrical circuit unless there is an initial current already roaming, right? But for this case, according to this graph, we do have an initial current here. Let's give it a name like I0. So initially, you could say that there is a current already roaming over this electrical element. This initial current is just I0. And then we suddenly gonna close this switch. At the instant at which we gonna close this switch, there will be more electrons coming, right? And there should be changes over the current, right? So the current will will start to change, because this, especially in case that this one is a function of time. So it means that the volt is already changing over the time. So that's why we are expecting the current over the electrical circuit is going to change, decrease, and then increase, then decrease, then increase, and so on, till it will reach after a while at a steady state. So initially, like for example, like you're starting the engine of your car. Once you start the engine, there is some vibration shows up in the engine till it will be steady, like just the initiation. So the transient behavior, this is the initiation of the electrical circuit work, right? Like once we switch or close the switch of this electrical circuit and we allow for more current to come in, there will be some deviation, severe deviation, till it will become steady. So there is a steady behavior that comes after the transient. All the time the steady behavior shows up after the transient region, right? The time period of this region is too small if we assume that this is like T1 and this is the time period of the T2. T1 is too small in comparison to T2. It means that the transient period, it takes just a few seconds, just part of a second even. Like as I told you, like once you switch on the engine of the car, it's gonna take like vibrate very hard, then it became steady very quick, right? So the vibration, the hard vibration at the instant of just turning the key of the car, this takes a few seconds, right? This is the transient behavior. Then beyond this behavior, after this few seconds, the engine became very steady. The same thing for the electrical circuit or any mechanical system, whatever it is, right? So this is the physical meaning of this transient behavior of the electrical circuit in comparison to the steady behavior. So that's why here we are interested to study this transient and the steady behavior. We should solve this equation. And this solution, it should be split into homogeneous and particular solution, or in other words, the transient solution and the steady state solution. Make sense? So now I'm going to show you how we can solve this equation, this first order ODE, mathematically speaking. Then we're going to repeat the same, but for the second order ODE. So how we can solve this equation, this first order ODE mathematically? As we said that we have homogeneous and particular solution. The homogeneous solution, if you remember from the mathematics class, for this equation, we're going to end up with this homogeneous solution if we just eliminated the right-hand side and just put this one by arbitrarily. We're going to assume that this is 0. This is going to give us the homogeneous solution. The particular solution can be obtained by considering a specific value for this right-hand side of the equation. So let us drive these two equations, two solutions, the homogeneous and the particular. So starting with the homogeneous solution, which should give us the transient solution. So the homogeneous solution, which is I homogeneous of T. You should understand that the same approach can be applied in case that would have the Vs, which is the voltage source, is the one that is unknown. So what you're going to do, you're just going to rewrite again this equation, but this right hand side is going to be 0 and you're just going to plug H as a subscript. So we're going to end up with the di H of T by dt plus the 1 over tau, the IH of T equals 0. This should give us the homogeneous solution. Solving this ODE simply gonna give us the homogeneous solution. How we can solve this equation? Simply if we try to move this one to the right hand side, then apply integration to both sides, we shall end up with a general solution for this ODE. So moving this one to the right hand side, we're gonna end up with DIH of T by dt equals the negative of 1 over tau, the I of T. Then we are going to integrate both sides. So if we did the integration to this right hand side, or simply we can do like, the key idea now, after we move this one and before doing the integration, let us do cross product kind of here, or collect the I terms in one side and the dt in one side, in the other side. So we're going to end up with, if you just move this dt here and you can switch this I of T in the denominator here. So we're going to end up with this expression like 1 over I of T di of T, but which I, it should be H homogeneous, right? Equals the negative of dt over tau. Then if you did the integration to both sides, this integration of 1 over x, if you remember from the mathematics, this gives us the ln, the natural logarithmic. So this is going to give us the ln, the natural logarithmic of IH of T equals the integration of dt, just going to give us T. So this is going to give us at the end negative T over tau, and tau is just a constant. So you're just going to carry on the 1 over T tau, and dt, the integration of dt gives T. Plus C, which it should be a constant, because there is a constant of the integration since we didn't plug the limits of this integration. So this should give us the integration. To get it, we are interested in finding how much is IH of T. So simply by applying the exponential to both sides to get rid of the natural logarithmic, so we're going to end up on the right hand side is IH of T, and this is the homogeneous solution. Is going to be the exponential term of the negative T over tau plus C, right? This time it can be split into like E negative T over tau plus E, right? Or times, should be like times E bar C, right? This e power c, simply we can assume that this is just a constant value, because whatever e power any value is, any number is gonna give us a number at the end, right? But anyway, it's gonna be like a constant. So simply let us consider this constant here like k, which k should be like e power c, no matter what is c is. Anyway, we're gonna end up with a constant. So at the end, we're gonna end up with this expression for the homogeneous solution, like it's gonna be the k, which is constant, times e negative t over tau. Again, the tau is the time constant and t just the time. So as you can see, we end up with the homogeneous solution of the current as a function of time. It depends on the exponential of negative t over tau, where again k is just a constant. This is a constant that can be determined, that can be obtained by applying the initial conditions. Make sense? So this is for this k just a constant. Your objective is to find this k value depending on the initial condition of the homogeneous current, right? So this is gonna give us the homogeneous solution. Now we're gonna move to the particular solution. So the particular solution, we're gonna repeat again, but in this case, we're gonna consider that the right-hand side will be f of t. We're just gonna consider, plug the right-hand side, then we're gonna use a subscript here of p stands for the particular solution. So what we're gonna do, we're gonna consider here the particular solution of the ODE, which it should be the I particular of t. Okay, so in this case, as I mentioned, we're gonna write the equation as the I of t, but particular by dt plus the 1 over tau, the I particular of t, it should equal to the f of t. Here we're gonna consider the f of t because this is the forcing term. The particular solution all the time is related to the forcing term. For some reason, if the right-hand side of the original equation, if the right-hand side of this original equation is from the beginning is 0, it means that in case that f of t equals 0, so there is no particular solution. Your solution is just gonna be a homogeneous solution and that's it, right? As I'm gonna show you right now. So what does it mean? It means that since we do have f of t, so we should have a particular solution, and we are seeking this particular solution. So how we can solve this equation? Let us follow this approach. One of the things we're gonna assume here, y, we're gonna assume y of t, which is a function, as integration function. We're gonna assume that this one is an integration function. And this integration function, it should be assumed that in such a way that make the left-hand side of this equation, is equivalent to the d by dt, y of t, I particular of t. So the key idea is just to arbitrarily assume this y. It would be any function. But what if the condition is, this function, it should be assumed under this condition. What is this condition? The condition that the left-hand side of this equation, which is di particular of t divided by dt plus 1 over tau I particular of t, it should equal to the time derivative of y times I particular. Okay, this is the method or the approach that we're going to use for solving, and this is the same thing that you should have before in the mathematics class. Okay, we are assuming this one. So the question is, how much is y based on this equation? So it is conventionally, or usually in this case, we have to solve this equation. But for y, not for I. As you can see, there is a problem on finding I here because it is ODE. But here this y can be simply solved. Why? If I ask you to do this derivative, this is the time derivative of the multiplication of two functions. So this left-hand side here is going to be dy by dt, right? Times IB of t. Make sense? All right. And, okay, let me check something here. This should be So the idea here is just, again, that we assume this y of t to be as an integration function that makes this term, which is d by dt, y of t, I b of t, which is the particular solution, equal to the left-hand side of this equation after the multiplication times y. Like we're gonna multiply here y in all of these terms. So we didn't change the equation. We still have the same equation. So we're gonna assume that this is the method that we have to come up with a value for y of t that makes this derivative term is equivalent to the left-hand side of this equation, which it should include here y and another y, right? Because if you added y times y here, you didn't change the value of this equation, right? Then what you're gonna do, you're just gonna decompose this derivative. So to have the derivative of the multiplication of two functions, this is gonna give us the dy by dt times ib plus the derivative of, or plus y of t times the derivative of dip of t by dt. Make sense? So if we put this term is equal to this term, as you can see, this should be like y of t. Just to make it much more accurate, you should understand that this y and this y is the y of t, right? This should be the y of t. So we're gonna have here y of t, and here we do have y of t. Make sense? So as you can see, do you see this term? It's typically identical to this term on the left hand side and right hand side. So they can be eliminated. Or I can write the equation again as dy of t by dt, I particular of t, plus the y of t, dip of t by dt equals this term, which is y of t, dip of t by dt, plus the y of t over tau times I particular of t. Make sense? As you can see that this term is identical to this term, so they can be cancelled together. So we're gonna end up with a function here like dy of t by dt, I particular of t equals y of t over tau, I particular of t, right? Also, this I particular can be cancelled with the I particular if you just divide by both terms. So we're gonna end up with this equation. Simply, if we did cross multiplication, just multiply this delta t here and bring the y of t in the denominator here, just cross multiplication of this function, the cross multiplication, this is gonna give us d tau times dy of t, right, equals the y of t dt. Then divide both equations by y of t. And even you can divide by tau, both equations, even. So we're gonna end up with this y of t will be cancelled. So on the right hand side, we're gonna end up with dt over tau. On the right hand side, dt over tau. And the left hand side, we're gonna end up, the tau will be cancelled with the tau with dy by y of t, right? If we did the integration to both sides, we shall end up with ln, the natural logarithmic of y of t, because this is y of t, 1 over y, equals this integration, which is going to give us t over tau. Make sense? It's going to give us the t over tau. And then if we apply the exponential, here there is no need to apply the add here a constant. Why? Because we are solving for y, not solving for I. The constant, if we're already solving for I, the current, we should add here a constant of the integration. But here we're just interested in the form of y of t, which is this function. We are seeking this arbitrary assumed function to be plugged here into this equation, right? So this y of t, if we apply the exponential to both terms, we're gonna end up that y of t, it should equal to the exponential of t over tau. So this is the y function that should be assumed or considered to make the left-hand side of this equation is equivalent to this term. Make sense? So now, by this y, if we plug this y into this equation, including the y, if we plugged y here with the e power 2t over tau, we're gonna end up that this left-hand side is gonna be identical to this one. right? So given this one, we can simply use this term directly. Like we can then say that the left-hand side, it became the d by dt of y of t, the I particular of t, equals the y of t times f of t, which is the right-hand side. So this is the new form of the equation, the original equation, but using y. This is the original equation, which is this one. I replaced this term with this term because we imposed this condition, right? So it means that this left-hand side can be automatically equal to this left-hand side, right? So this left-hand side equal to the y times y, and we already got that value, got a specific value for. Now let us apply the integration to both sides. So this integration is going to get rid of the derivative, right? If we did the integration, the derivative will be cancelled. So we're going to end up on the left-hand side just y of t, I particular of t equals the integration, which is the integration of y of t, f of t, right? So how much is y of t? Y of t, we already got it by e. So we are doing, keep in mind that we're already doing the integration with respect to the time, right? As dt to both sides, plus constant, because here we're going to do the integration of a term that would already include I, so there should be a constant of the integration. How much is y of t? Y of t we already got it as exponential to the power t over tau. So plug this value here. So we're going to end up with e power t over tau times I particular of t equal the integration of e power to t over tau times f of t dt plus constant. Make sense? If we divided, since we're already interested of I particular, so we have to divide all the terms by this exponential term, divide all the terms by the e power to t over tau, e t over tau, and the same thing here, e t over tau. So we're gonna end up with e t power to t over tau in the denominator can be moved in the numerator by switching the sign of the exponential. So this one anyway will be cancelled, so the left hand side will be I particular of t will equal to this one. It is 1 over e t negative over tau, so it can be written as e negative t over tau, right? Times the integration of e t over tau times f of t dt plus constant, which is just c times e, or any constant like k, for example. We can assume this one like k. We can, instead of using, you can use any letter like k, e negative t over tau. This should be tau. All right. So this is gonna give us the particular solution. So we got here the form of the particular solution in terms of t as a function of time, in terms of f of t, which it should be the right hand side, and tau, right? Then if we added both of these terms together, if we added these two terms together, we shall end up with we shall end up with the total solution. So the total solution here, I total of t equals, it should be the I homogeneous, which we already got it, plus the I particular. The homogeneous solution, we got it here with this value as k e negative t over tau. You could consider this is like k1. And we already got here another k, like k2, right? This is like k2. So if we added this one, just to distinguish this constant from that constant, right? The k up there. So the homogeneous solution, we get it as k1 e negative t over tau, plus the particular solution, we get it with this expression as e negative t over tau times the integration of e t over tau f of t, which is the force function dt, plus the kt e negative t over tau. As you can see, this term is identical to this term except the constant itself, right? It means that we can combine these two terms together using the e negative t over tau as a common factor. So this is gonna give us, if we combine both of them together, we're gonna end up with this expression. I'm gonna move it step by step. So the total current is gonna be the k1 plus k2 both times e negative t over tau, plus e negative t over tau times the integration, which is e to the power t over tau f of t dt. How about if I assume that these two constants just K? Another constant, because these just two numbers like 2 plus 5, and we don't know their values yet, and we don't care how much is exactly K1, how much is exactly K2. I can combine both of them in just any one constant. So it means that we're gonna end up at the end with this expression of the total current, that it's gonna be even this e bar to the power negative t over tau. I can consider this one as a common factor, so we're gonna end up with e to the power t over tau times k, which is just any constant that can be obtained by applying the initial conditions, plus the integration, which is the integration of t to the power of t over tau, times the f of t, which is the forcing term or the right hand side of the equations. This is going to give us the general solution of the current for the first order ODE. Make sense? So this is the derivation. This is how we drive this solution. This procedure, all of this procedure that I explained to drive this solution, you are not required to write this derivation all the time for all the problems. No, we are interested. I just showed you how we can drive this analytical solution, that the drive from now on, that you should understand that the general solution of this first order ODE is gonna be the one that we drive it up there. That it depends on tau. Your objective is just to form tau, is to form the f of t. Then you're gonna directly plug into this expression for the total solution or the general solution of the total current, which is I of t as a function of time. Where k, it should be initial condition that can be obtained by, it is a constant that can be obtained by applying some initial condition. What is the initial condition? For example, that he gonna state to us that the current initially was 0. Once we switch off on the electrical circuit, we said that we do have this drawing, right? And this is like, there is a switch here. At the instant that we're closing the switch, what is the value of the current? Is it 0 or is it have a value? If it has a value, we can, whatever, it is 0 or a value at the initial condition, at the instant that we close the switch, we close the electrical circuit, we allow for more current to come in. If there was any initial current or not. If there is, we're gonna plug a value at t equals 0 with the value that is given. If not, we're gonna plug I at t equals 0 as 0. To solve or to find only one constant, which is k. Since we do have only one constant, it means that we just need only one initial condition. So only one initial condition can be used in finding this constant k. So I'm gonna give you an example here. An example of, assume that we do have RC electric circuit with Vs of t equals 10t. So simply the Vs, which is the voltage source, it is a function of time, right? And whatever the value of R or C is, it is required to find the current function if I of 0 was 5 ampere. So what does it mean I of 0? This is the initial condition that I'm talking about. Like at the instant of t equals 0, there was a current within the electrical circuit. This current was with 5 ampere value. So how much is the current as a function of time? We need the current function as a function of time. So your objective simply is just to write the equation of the RC circuit. What is the RC circuit? The equation, if you go back here, we said that for any RC circuit, this is going to be the equation, di by dt plus 1 over RC times I of t equals 1 over R dv by dt. And tau for RC circuit is going to be RC, and the function, the f of t, the right hand side is going to be 1 over R dv by dt. Make sense? So simply I can write the equation into this form using the tau and the f. But for the RC circuit, you should understand that the tau, it should be the RC, and the f of t should be the dv by dt time divided by r. So I'm going to use these expressions here. So since for RC circuit, we knew that that the di of t by dt plus 1 over tau I of t equals f of t. This should be the equation. The first order equation gives us the electric circuit equation. This is the electric circuit, or the circuit equation directly. This is the circuit equation. This is what we knew up there, that for any RC circuit that includes just R and C, its electric equation or circuit equation is going to be a first order ODE with this form, where tau, it should be the R times C, and the f of t, it should be the time derivative of 1 over R times the dVs of t by dt. For this function, Vs of t was given by 10t. T is the time, it's given as a function of time. So simply you're gonna divide this, the derivative of this 10t gives just 10 divided by R. So this is gonna give us, it means that the f of t is gonna be 10 divided by R. This is gonna be the f of t. It is just a constant value, and the tau is just a constant value. Why it is constant, not a function of time? Because R is already a constant. Then simply you can find the solution. The solution of this equation, whatever the value of tau is, whatever the value of the f of t, the force is, plug these values that we got for tau and f of t into this equation. You're gonna end up directly with the total current. So simply the total current I of t, according to this equation, is gonna be E negative t over tau times k, which is just a constant that we have to find this one using the initial condition, as I'm going to show you the integration of e power to t over tau. You have to memorize this expression times the f of t dt. This should be the expression that we drive it for the total current. Then your objective is just to plug the value for tau and for f of t into this expression. So simply we're going to end up with this equation. So the I of t, then I of t, it will be e to the negative t over tau. How much is t? Tau, it is RC. RC, should be values. For example, if I give you R with a value, C with a value, so you're gonna substitute for R and C. C, which should be the infrared, and the R, it should be in ohms. This is the resistance and the capacitance of the RC circuit. Times K, which it should be constant to be found, and the integration of e to the power t over tau times f, which is just a constant value as 10 over r. So this 10 over r, I can carry on this 10 over r outside the integration because it is just a constant value. So moving this out, outside the integration, this is going to give us 10 over r dt. Then your objective is just to solve this integration. What is the integration of e exponential t over tau? This gives us the exponential, the integration of this one gives us the exponential of t over tau, and then you're going to divide by the derivative of this exponent. The derivative of t over tau gives 1 over tau. So you can move this tau on the top, so this is going to be equivalent to tau times e to the power t over tau. Then substitute here. So this is going to give us at the end the total current I of t equals e to the power t over RC times K, which is just constant, plus 10 over R times the integration, we got it tau. Tau we got it before as RC e to the power t over RC, because we just got tau up there by R times C. So simply this R can be cancelled with this R to end up just 10C times e to the power t over R over C. Make sense? So this is the current, but in terms of K. How much is K? We have to find this K. So in this case, we have to apply the initial conditions. The initial condition, would have only one initial condition, that the current when T equals 0, it should equal to 5 ampere as already given, right? So what does it mean? When I of 0 equals 5, according to the given initial condition, your objective is just to plug T equals 0 into this equation. So e to the power of 0 is just 1. Anything to the power of 0 is just 1. So this is going to give us 1k plus 10 times c times e to the power of 0 gives just 1. Anything bar to the 0 is going to be 1. So in this equation, this is a very simple linear equation that can be simply solved for k. So solving for k, This is gonna give us the constant K, how much it is. So K is gonna be just moving the 10C to the left hand side. So this is gonna give us 5 negative 10C. Where C again, this is the capacitance. It is not a constant. This is the capacitance of the capacitor. Then plug this value of the constant K that we got here into this equation to end up that the total current I of t is gonna be this form as e to the power negative t over RC times 5 negative 10C plus 10C e to the power t over RC, and that's it, right? This is the equation. I just plug this K with its value here. So this is gonna give us the current as a function of the time. If we use, for example, MATLAB, we can plot this current, so we're gonna end up with a curve on the time on the horizontal axis, and the current is gonna be on the vertical axis. And this curve is gonna look like, for example, like this way. It would be in this way. So you're gonna have like some transient period, then you're gonna have a steady state period, kind of. Or it would be represented in this way, in this form, going down, then up, then you're gonna have a steady state. This is an option. Or it would be showing just going down and that's it, decaying and that's it. Or it would be, it's gonna go up somehow, then it's gonna drop down again to a specific value. So a constant value, I mean. So it's gonna be this way. So we could say, in this case, we're gonna say that this is the transient period, this is the transient, and this is the steady state. Make sense? So it would take any different form. For example, where you should understand that this is the initial condition, this is the 5 ampere, this is the initial condition of the current, or even it would go down, then it's gonna go up. It depends. So there are lots of things, depending on the value of R, depending on the value of C. As I'm gonna give you an example with some values for R and C. And even I'm gonna show you how we can use MATLAB to draw a curve, to draw this function using MATLAB, and then we can read some data. We can do changes and study the effect of the R, the effect of the C, how the R, how about if we increasing the R, what's gonna happen to this curve? This curve describes the response of the electrical circuit or the variation of the current through the electrical circuit. This is what we're gonna explain in another video. But the objective for now is just to show you how we can drive the solution of the first order ODE, and this is what we got here, right? So from now on, you don't need to write all of this derivation of the first order ODE, all of this mathematics, forget about it, okay? Your objective is just to understand and memorize this expression, like this one. Like the general solution of a first order ODE, it's gonna be in this form. From now on, your objective is just to form the value, how much is the F of t, how much is tau, depending on the given electrical circuit. Then your objective is just to plug tau and F of t into this equation to solve for the current. Make sense? So this is simply how we can solve the first order ODE. Now we shall be moving to the second order ODE, but this will be covered over another video. So the next video we're gonna discuss, I'm gonna show you how we can solve the second order ODE, but then after that we're gonna study how we can do analysis for these two ODEs, the first order and second order, and we're gonna study how the R, how the C would affect the behavior and the transient response or the steady state response, and we're gonna discuss what does it mean response of this electrical circuit. This is what we are going to discuss in the next video. Thank you.